Good evening, everyone. Welcome to my 11th class in this series. Up to the 10th class, we have learned about the aromatic compounds, aliphatic compounds, these things. In the last class, we have discussed about what are aromatic compounds and how to find out a compound as an aromatic or an aliphatic. So we have also discussed about the aromaticity of compound. After discussing about the aliphatic and aromatic compounds and their aromaticity of the aromatic compound, we are now to discuss about some properties of benzene. So how benzene actually behaves if it does not react with the normal addition reagents. We have seen in the last class that although it contains three double bonds, benzene contains three double bonds, but it does not behave like a simple triene, like the aliphatic unsaturated hydrocarbon. So the quality that makes it different from those aliphatic compounds is known as aromaticity. And in the last class, we have also learned about how we can differentiate between an aliphatic and aromatic compound, because aromatic compound is the one which is characterized by its fragrant smell, coming from the Greek word aroma. So first discovered aromatic compound was benzene in 1825, which was in 1845 Holman discovered from coal tar, which contains benzene and many of its derivatives. Now, in the last class, we have told you that benzene generally does not undergo addition reaction. Why? The three double bonds benzene contains, it's not like the double bond as the simple alkenes or simple pi bonds, although it contains three pi bonds. Now, what are the chemical properties, or what are the reactions that benzene will actually show? Now, we are going to discuss this particular thing in this class. Here you have seen in the slide the reaction actually shows by benzene or aromatic compounds is electrophilic aromatic substitution reaction. You know why? Because after showing electrophilic aromatic substitution reaction, the aromaticity of the aromatic compounds is retained. It is not lost. That's why it always tends to show the electrophilic aromatic substitution reaction, because it does not allow the compounds to lose their uniqueness. That means aromaticity. Okay. Now the five aromatic compounds, the five aromatic substitution reactions generally shown by benzene I have listed out here, that are known as nitration, sulfonation, halogenation, alkylation, and acylation. So these are the five electrophilic aromatic substitutions shown by almost all types of aromatic compounds. So you will have to know these reactions one by one. First of all, nitration. The reagent used for nitration is concentrated mixture of concentrated nitric acid and concentrated sulfuric acid. The electrophile, since it is electrophilic aromatic substitution, so one of the H plus will be substituted by NO2 plus. The electrophile here is NO2 plus, that is nitronium ion. That's why reaction is called nitration. In the next reaction, you will see the name is sulfonation. The reagent is concentrated sulfuric acid. Since here the electrophile involved in this substitution to replace the H plus is SO3, therefore it is known as sulfonation reaction. In the next class, it is known as in the next reaction, it is known as halogenation. Since the H plus here is substituted by a halogenation, if it is replaced by Cl plus, it is chloronium ion, then it is will be known as chlorination. Here it is, this halogenation is a chlorination, since H plus is substituted by Cl plus chloronium. If it is replaced by Br plus, it will be known as bromonium, I plus iodinium, F plus chlorination, iodination, etc. Okay. The reagent required for halogenation is the FeCl3 halogenation plus FeCl3 catalyst. Next reactions are alkylation. So it is known as alkylation because H plus is substituted by a alkyl group. The reagent required is haloalkane and AlCl3. Next, acylation. It is known as one acyl chloride and AlCl3. The H plus will be replaced by the electrophile acyl cation. Therefore, it is known as Friedel-Crafts acylation. Okay. Now let us discuss the mechanism of these five reactions one by one. The mechanisms are very important, but one interesting thing is that all the mechanisms are almost the same. We will show the mechanism from the next lesson onwards. So this is the general mechanism. I have already told that these five reactions follow the same type of mechanism. So I am showing here first of all a general mechanism. Then I will go to the individual mechanisms. Okay. So whether it is nitration, whether it is sulfonation, whether it is acylation, alkylation, whatever. So the electrophile I am terming here is E plus. So benzene has 3 double bonds. One of the double bonds will attack at this electrophile. The mechanism, the initiation of the mechanism is similar to that of Markovnikov rule. We have discussed about how the reagent is attacked by the double bonds in the while discussing about the Markovnikov rule. The same is happening here. This is Plassey effect. Okay, the one of the double bonds will attack the electrophile. Whenever the double bond attacks the electrophile will get attached to one of the carbon. Then and the other carbon will become positively charged. Now this carbocation or sigma complex is stabilized by resonance, because after formation of this cation, this will be stabilized like this. Plus will be now here. Now this plus will be stabilized by this, then plus will be now here. So the plus charge is not localized, it is, but in fact it is delocalized over several carbon atoms. Therefore this sigma complex is stabilized by resonance. Okay, in the last step what will happen, in the second or last step what will happen, proton transfer will take place. In the resonance the resonance structure, the base will attack at the proton will be eliminated, and the bond will be uh, delivered to the electron deficient ring. So a double bond is now regenerated. So the aromaticity requires 3 double bonds, as we have discussed in the Huckel's rule. Benzene contains 3 double bonds. In the original benzene it has 3 double bonds, 4n plus 2 rule satisfied aromatic. In the last molecule also it contains 3 double bonds satisfied aromatic. Okay, so we have seen that during this mechanism, whatever the electrophilic aromatic substitution reaction is, that the aromaticity of the reaction is aromaticity of the compound is retained. Therefore it always benzene and benzene like compounds always favors electrophilic aromatic substitution reactions. Now let us go to the individual reactions. First of all, halogenation. So in the halogenation reaction we are having the reagents halogen and Lewis acid catalyst. Here we are going to discuss about bromination. So it is FeBr3 and Br2. So Br2 attacks the FeBr3 molecule. This is a Lewis acid. So this has become FeBr4 minus. Now the FeBr4 minus is detached here. Whenever FeBr4 minus is detached, then this Br plus becomes released. It will release as an electrophile and will attack at the benzene to get the resonance stabilized sigma complex. Now in the last step, as we have the last step involves elimination of proton. Now this proton is eliminated here by the conjugate base FeBr4 minus. This FeBr4 minus eliminates the hydrogen as proton, and this bond is delivered to the electron deficient sigma complex. Now the aromaticity is retained and it becomes bromobenzene. This is very simple. So the reaction involves basically 3 steps. The first step involves the release of the electrophile, how the electrophile is generated from the reagents. After formation of the electrophile, it will attack the benzene to form the sigma complex in the second step. In the third step, deprotonation or proton elimination will take place to regenerate the benzene. Okay, the 3 main steps are involved in all the 5 aromatic substitution reactions we are going to discuss here. The first we have discussed already is halogenation. Next we are going to discuss is nitration. Okay, what are the reagents for nitration? It is a mixture of concentrated nitric acid and concentrated sulfuric acid. Now, sulfuric acid plays an important role in nitration reaction because this is the structure of nitric acid. This is the structure of sulfuric acid. Now, sulfuric acid attacks at the nitric acid molecule so that the NO2 plus molecule release. NO2 plus molecule, that means this electrophile is required for this reaction. Ultimately, the NO2 plus or nitronium ion electrophile is generated. Now this nitronium ion attacks the benzene in the second step, so sigma complex is formed. This is resonance stabilized. And in the step 3, the water molecule will attack at the proton and will be eliminated as H3O plus. Ultimately this bond will be delivered to the electron deficient benzene ring or sigma complex, and ultimately we are getting the 3 double bonds, that is the aromatic structure, and NO2 gets attached to the ring. Okay, also ultimately we are getting nitrobenzene. So this is nitrous. Next, sulfonation. One interesting feature about sulfonation is that the electrophile here is SO3. This is SO3. So SO3 is a neutral electrophile. So this is interesting. That's why the sulfonation reaction, you will see that this contains one additional step. In general, electrophilic aromatic substitution reactions generally have 3 steps, but here you are seeing that here there are 4 steps. This is because of the involvement of one neutral electrophile. Okay. So the first step, what was the reagent for sulfonation? Concentrated sulfuric acid. Well, so sulfuric acid, one sulfuric acid reacts with another sulfuric acid molecule to get sulfur trioxide, hydrogen ion, and HSO4 minus. This is the conjugate base. So conjugate base of sulfuric acid. Okay, now this SO3 is an electrophile. It is in fact a neutral electrophile. This neutral electrophile will be attacked by the one of the double bonds of the benzene. Now this is become the sigma complex is formed. The one negative charge is present on the O minus because it was originally SO3 molecule was originally a neutral molecule. Now since the electron source is attached to the sulfur, therefore it becomes negative because of reason. Okay, now the conjugate base SSO4 minus comes to the picture in the step 3 as always. So this hydrogen becomes eliminated and SSO4 minus, that is the conjugate base, becomes the original acid, that is sulfuric acid. Now this bond is delivered to the benzene, so the benzene is regenerated. Ultimately we are getting the benzene and SO3 minus attached to this. Now since SO3 minus is reactive, therefore it is getting protonated by another sulfuric acid molecule in a first step to get the ultimately benzene sulfonic acid, that is SO3H group attached to the benzene. Benzene sulfonic acid is formed. This reaction is known as sulfon. Now these are the two reactions discovered by Friedel-Crafts. Therefore, these reactions are known as Friedel-Crafts alkylation and Friedel-Crafts acylation. Mechanism is almost similar to both of them, so we are putting both the mechanisms in the same slide. Now let us see what is happening in Friedel-Crafts reaction. First of all, see the alkylation. So for the alkylation, we are requiring a alkyl halide. Will attack with react with AlCl3, the Lewis acid catalyst, to get the AlCl4 minus, that is the conjugate base of AlCl3. So ultimately we are getting R plus, or here the R plus is H2-C plus. So this is alkyl carbocation. So this alkyl carbocation is now acting as an electrophile. Now this electrophile will be attacked by the one of the double bonds of benzene, and we are getting again the region stabilized sigma complex. Now the proton present in the sigma complex adjacent to the alkyl group will be eliminated by the conjugate base, that is AlCl4 minus, and will be converted into the original Lewis acid, that is AlCl3. So the three double bonds are regenerated because the while abstracting the proton, the original CH bond was delivered to the benzene, deficient benzene, and three double bonds were regenerated. Ultimately, we are getting the alkylated benzene. So this is known as Friedel-Crafts alkylation because since one alkyl group is attached to the benzene. Now similar to this, we are seeing here acylation. Only the difference is the reagent. Here alkyl halide is not used, here it is acyl halide is used. All other things remaining same. Ultimately we are getting that acylium ion or acylium cation acting as the electrophile will attach to the benzene, and we are getting the acylated benzene or one aromatic ketone. So this is known as Friedel-Crafts acylation. Now something about the orientation of effect of substituents and activity. It has been seen that some groups are saying that the incoming electrophile will attach the ortho and para position, and some will tell you that it will attack the meta position. Here it is attacking the meta position. Why it is so? You will have to remember this, because these groups are ortho para directing, these groups are meta directing, these are ortho para directing but deactivating. Why it is so, we'll see one by one. Now let us see if one ortho para directing group, this is OH group attached to the benzene. If we this is attacked by an electrophile like nitronium. If we see, then we will see that in case of ortho and para attack, structures 4 and X, this and this are shown that the unshared electron pair of oxygen delocalize the positive charge on the carbocation, and hence 4 resonance structures are possible. So here 4 resonance structures are formed in the ortho attack. In the para attack also 4 positions are attacked, so therefore ortho para positions will be left. Similarly here 4 meta will be preferred. You will see later on. These are some additional reactions we have. So lastly, we are giving you some homeworks for you. Predict the major and minor product. Nitration of bromobenzene, well, orthopara will be major product, okay. Nitration of nitrobenzene, meta will be major product, okay. Bromination of nitrobenzene, meta will be major product. Chlorination of fulminate, orthopara will be major product. Similarly, we are giving you some completion. If you find any difficulty, then you may contact me later onwards. Okay, this is all about the reactivity of benzene. This is all about today's class. We'll see in the next class about the heterocyclic compounds and the polycyclic aromatic compound. Till then, thank you. Bye bye.